Hi everyone, we now present our CVPR 2026 paper on LiDAR-to-4D radar diffusion bridge via cross-modal alignment and translation in latent space. 4D millimeter wave radar sees through fog, rain, and snow, but collecting 4D radar data is prohibitively expensive. So we ask, can we generate full 4D radar, including Doppler velocity, directly from cheap, off-the-shelf LiDAR? In this work, the answer is yes. 4D radar uniquely captures range, azimuth, elevation, and Doppler velocity all at once. Prior synthesis methods only produce 2D or 3D slices and discard Doppler entirely, losing the information that makes radar valuable. We are the first to generate the complete 4D tensor. Concretely, our task maps a sparse 3D LiDAR tensor to a dense 4D radar tensor, both in their native polar coordinates. Look at the gap. Radar signal power spans 14 orders of magnitude, and while LiDAR is 99% empty, radar is fully dense. These two modalities are fundamentally different. This leads to three challenges. 1. Model the high-dimensional, noisy radar distribution. 2. Bridge the huge sparsity gap between modalities. 3. And most fundamentally, invent Doppler velocity from purely spatial LiDAR cues, since LiDAR has no velocity information at all. Our framework, L2RLDB, addresses these in three stages. First, we compress 4D radar into a compact latent space. Second, we align LiDAR into that same latent space using contrastive learning. Third, we translate between them with a Brownian diffusion bridge. Let me walk through each stage in turn. Stage 1, the key voxel-aware radar VAE. Only about 1.5% of voxels carry real object returns. We use CVPR detection to find these key voxels, keep their full Doppler vectors, and model the rest as Gaussian background noise. The decoder has three heads: a key voxel mask, a Doppler mean map, and the Doppler tensor at key voxels, with an L1 loss on absolute power values to handle the huge dynamic range. Stage 2, we align LiDAR into the radar latent space. A twin VAE encodes LiDAR with exactly the same latent shape. Then patchwise contrastive learning enforces that the LiDAR latent at each spatial location matches its paired radar latent and differs from all other locations. This gives us a semantically and spatially aligned cross-modal space. Stage 3 is the heart of our method, the Brownian diffusion bridge. Instead of conditioning a standard diffusion model on LiDAR, we formulate translation as a Brownian bridge process directly between LiDAR and radar latents. The interpolant smoothly transitions from radar at time 0 to LiDAR at time 1 with controlled noise in between. A 3D UNet learns the drift, and a DDIM-style sampler enables fast, non-Markovian inference. Crucially, this avoids the domain gap problem that plagues conditional diffusion. On the K-radar benchmark, 35,000 LiDAR radar pairs across 6 weather conditions, L2RLDB outperforms every baseline. Two key observations. Latent space methods beat pixel space methods, confirming alignment matters. And our diffusion bridge beats conventional conditional diffusion, confirming the bridge formulation matters. Now the headline result. We use our synthetic radar to train a downstream 3D detector. With only synthetic data, we reach over 90% of real data performance, proving the synthesis is faithful enough to replace data. And when we use synthetic data to augment real radar training, detection AP3D increases by up to 16% at the strict IOU threshold. Across all 6 weather conditions, normal, overcast, fog, rain, sleet, snow, augmentation gives consistent gains. Qualitatively, our generated radar closely matches ground truth across normal, overcast, rain, and snow conditions. Power maps align, Doppler bins align, and key object voxels, shown in green, correctly localize vehicles and road curbs in every weather. To summarize, L2RLDB is the first method to generate full 4D radar from LiDAR via a latent diffusion bridge. It improves both generation quality and downstream detection by up to 16%. Code and paper are available. Scan the QR code. Thank you for watching.